Hello, everyone. This is Calculus Lecture 15. This is the very last lecture, and today we're just going to go over everything we've done so far. So we started out talking about limits and continuity. So if a function value is approaching something, so we have some function, and at some point, the function is approaching that value from both sides, then we say that the limit of the function as x approaches this value is the value f is approaching. If it only approaches from one side, we might say a left or right limit approaches this value. Now, a function is continuous at a point if the limit exists and equals the value of the function. We say a function is continuous if it's continuous at every point where it's defined. So right-hand limits coming from the right, left-hand limits coming from the left. If both exist, then we have a total limit. We can also take limits as x approaches infinity. So that's basically telling us what value does f of x approach as x gets bigger and bigger. Similarly, we could take a limit as x approaches negative infinity. So what value does f of x approaches as x gets arbitrarily small? Sometimes the limit itself might be infinite. So if you're approaching some value and then we have an asymptote, or if it's just going off to infinity, then we can say that the limit is plus or minus infinity. But in that case, the limit still doesn't exist. We just use that notation anyway. So limit exists always means that it exists and is a finite number. For polynomials specifically, we just have to look at the leading coefficients to look at the end behavior. So as x goes to infinity, we're just going to look at whether the leading term is positive or negative. If it's positive, then the polynomial will go to plus infinity. If it's negative, the polynomial goes to minus infinity. On the left side, so as x approaches negative infinity, it's also going to depend on whether the degree of the polynomial is even or odd. If it's even, then you just look at the leading coefficient, same as the positive side, because a negative number to a big even power is still going to be positive. If it's an odd number, then we flip the sign, because a negative number to an odd power is negative. We have our definition of continuity. Every polynomial is continuous. We have sums, differences, products, compositions of continuous functions are all continuous. When we have a continuous function, the limit equals the function value. And usually, if given a graph, we won't do the very formal definition, though there is one. If you want to look into it, it's called the epsilon delta definition. But if we just are given a graph, we can tell whether it appears to be continuous by just checking that it doesn't have any breaks or holes or any gaps, really. All right, then we talked about finding the derivative. So the derivative is the rate of change of a function. We have some different notations for the derivative. So we have f prime of x, dy dx, and d dx. By definition, the derivative is equal to the limit as h approaches 0 of f of x plus h minus f of x over h. So we use that at first, but then we had a lot of rules for finding derivatives because this definition turns out to be quite tedious. So particularly for polynomials, we have the power rule, the derivative of x to the n. For any n, even if it's not an integer, is equal to n x to the n minus 1. That's very important. Right? And the derivative tells us the slope of the tangent line to a function at that point. So basically, we have our function, we have some points, and then the slope of this line is the derivative at that point. And this is how we came up with this function, by approximating the slope by picking 2 points very close to each other and taking the line joining them. And so this is the definition of derivative. I'm just going to start out. It's super important. And sorry, a function is differentiable if the derivative exists at every point. In general, that just means it doesn't have sharp corners and it has to be continuous. If the derivative exists, a function will always be continuous. The tangent line, if the tangent line is vertical, then the slope is undefined. And so the derivative does not exist at that point, and the function is in fact not differentiable at that point, even if it appears totally smooth. Yep, and here's our power rule. We can always add and subtract derivatives, and if we have a sum and we're taking the derivative, we can just take the derivative of each term separately. That's totally fine. We also have multiple higher order derivatives, so we can take the second, third, fourth derivatives. Remember our notation for that, so we could use like f double prime or f triple prime for a second or third derivative. For higher powers, we would want f and then the number in parentheses. Or we could do like d squared x, or sorry, d squared y over dx squared, or change the two to whatever order derivative we want. We have the product rule for derivatives, so d dx of f of x times g of x is f prime of x times g of x plus f of x times g prime of x. So you differentiate the first guy and multiply by the second guy. Then you differentiate the second guy and multiply by the first guy, and then you add those two. The quotient rule tells us what to do if we're looking for a derivative of a quotient, f over g. So remember, the best way to remember it is low d high minus high d low over low low, where d represents taking the derivative. That's how my calc teacher did it. And so this is basically telling us that the derivative equals gf prime minus fg prime over g squared, assuming g is not 0. Of course, if g is 0, then this isn't defined, and neither is this because the denominator is 0. Here's some common derivatives of trigonometric functions that are good to remember. So the derivative of sine is cosine, the derivative of cosine is negative sine. You don't have to remember the other ones because you can just work them out using the quotient rule. That's what I do. But if you prefer to remember them, you can. So here they are. And then here's the derivatives of the inverse trig functions. If you want to copy those down, I'll wait for a moment. Derivative of the natural log of x is 1 over x, and the derivative of e to the x is e to the x. Those are good ones to keep memorized. They're very important. Right. And then we have implicit differentiation, the chain rule. So if we have a composite function, f of g, and that's the same as this, so then the derivative is f prime of g of x times g prime of x. So you differentiate the outermost function and evaluate at the inner function, then multiply by the derivative of the inner function. So here's just a quick example. We have y equal to this. And so we can write this as the composition of f of x equal to 4x squared and g of x equal to the inside thing, so x squared minus 3x. And using the formula, we're going to take the derivative of f, which is 8x, but then evaluate at g of x, so 8x squared minus 3x times the derivative of g of x, which is just going to be 2x minus 3. And then we can also like graph the derivative. We can look at second derivatives, which tell us about concavity. So remember that we have a graph that's concave up if the second derivative is positive, and concave down if the second derivative is negative. And we can also use the first derivative to look for minimums and maximums. We learned about implicit differentiation. So sometimes you can't isolate y in terms of x, but you still want to find dy dx. So you can differentiate directly, basically using the chain rule. So for example, here we have y squared minus 3y plus 2x equals 3. So we can differentiate in terms of x. So we first differentiate the outer function with respect to y. So that gives us 2y times the derivative of y with respect to x, which is dy dx, right? Minus 3, which is the derivative of 3y with respect to y, again times dy dx. because we need to take the derivative of y with respect to x, right? Plus the derivative of 2x, which is just 2, equals the derivative of 3, which is just 0. And we could use that to solve. Sometimes the variables might be different. You might be using dx dt, du, whatever it is. So don't mix those up. It doesn't really matter. It's just the same process no matter what the variables are. And you can use the quotient rule if you need like a second derivative, say. So the derivative from the example above works out to this. So you could differentiate and use the quotient rule to get another a second derivative. We also have a derivative of an inverse function, which is 1 over the derivative of the function value. So this is a formula. This one's good to have in mind. Sometimes the derivative has applications in physics. So, for example, the velocity is exactly the derivative of the position. The acceleration is the derivative of the velocity. So you can find those if you know the position. If the velocity and acceleration have the same sign, then the object is speeding up. If they have opposite signs, it's slowing down, regardless of whether the signs themselves are positive or negative. So if the sign's positive, then it's speeding up in the positive direction. If the sign's negative, it's speeding up in the negative direction. Sometimes you might see related rates problems. I don't think we did this, but basically you might have a word problem like this. So a circular pool of water is expanding at the rate of 16 pi square inches per second. At what rate is the radius expanding when the radius is 4 inches? So basically, we have our derivative. And then we can just solve for it. I'm not going to go over this in too much depth, but you can look into it in the textbook. Once we do have a derivative at a point, we can get a linear approximation for the function. So we have our graph and some point, then the tangent line at that point is sort of a linear approximation that's close to the graph of the function, very near that point. And you'll learn in BC Calc about Taylor series and Maclaurin series. So when you do those, you're going to take not only the first derivative, but higher order derivatives. So the second derivative, the third derivative, even infinitely many derivatives. And you'll get a really, really close approximation to the function. We didn't actually do L'Hopital's rule, but this is important to know. So if you're taking a limit of a quotient, so the limit is x goes to a of f of x over g of x, and what you're getting is that the limits of both f and g are both 0, or they're both infinity, so it's giving you one of these indeterminate forms. Then you're allowed to do this thing where you just take the derivative of f and of g. And you'll be able to take, you can just take the limit of that, and the limit will be the same as the original limit. So here's an example. Let's do the limit as x goes to 0 of sine x over x. Then, so sine x as x goes to 0 is going to 0. I'm just going to put this in blue because it's not like equal, but like just the indeterminate form. And x is also going to 0. So that's giving us this 0, 0 indeterminate form. So now we're allowed to use our L'Hopital's rule. And so this is the limit as x goes to 0 of the derivative of the top, so that's cosine x, over the derivative of the bottom, which is just 1. So it's the limit as x goes to 0 of cosine x. And cosine of 0 is just 1, and it's continuous, so the limit is actually 1. So this would be a pretty hard limit to do by hand, but L'Hopital's rule simplifies it considerably. Here's another example if you want to try for practice. We talked about the mean value theorem just last lecture. So if we have a function that's continuous on a closed interval from a to b and differentiable, when I said it, I stated that it was differentiable in the whole closed interval, but it does not technically need to be differentiable at the endpoints, just on the open interval from a to b. Then there's a point between a and b where the derivative at that point is equal to the average rate of change, which is the slope of the line connecting a comma f of a and b comma f of b. So basically there exists some c, so that f prime of c is f of b minus f of a over b minus a. We have our special application, which is when f of b equals f of a, and then we have some function, some value c, so that f prime of c equals 0. And that special case is called Rolle's theorem. Here's the image we had for the mean value theorem. So if we have 2 points, here's the line connecting them. And then we're saying there's some point where the tangent line has the same slope, so it's parallel to the secant line. We have the extreme value theorem. I'm not sure if we covered this, but what this tells us is if we have a closed and bounded interval, so from a to b, and f is a continuous function on a to b, then f takes an absolute maximum and minimum value. So there's some value where f of x is the maximum over that interval and some value where it's the minimum. This does not have to hold if we're working on an open interval. And here's why, because if we're working on an open interval, say on this, then we can have f be like this and not defined at the endpoints. But we can see there's really no maximum because we can't pick any point on the line to be a maximum because there's always one point higher. And the endpoint isn't on the graph, so we can't actually pick that. But if we pick anything that's lower than it, then there's something that's just a little bit higher. So we do need it to be a closed and bounded interval. And later on, if you study, say, topology, we're going to call these guys compact. Right, critical point of a function is any point where the derivative is 0 or it doesn't exist. And critical points are useful because they're going to help us find minimums and maximums. So we know that if there's any minimum or maximum of a function, say here, then the tangent line is horizontal, so the first derivative has to be 0. Now, that does not mean that anytime the derivative is 0, we have a minimum or maximum. The reason for that is that sometimes we could have a function like this, where even though the derivative is 0 at this point, it doesn't change from increasing to decreasing or decreasing to increasing. So to figure that out, we use the second derivative. So if the second derivative is positive at the point and the first derivative is 0, then we're at a local minimum. And if the second derivative is negative and the first derivative is 0, then we're at a local maximum. And if both are 0, the first and second derivative, then we don't have either, actually. Then we are going to be in a case that looks like this. So the function's just going to keep on increasing or decreasing. It just like slowed down to 0 for a second and kept going, instead of like slowing to 0 and turning around. A point of inflection is a point where the second derivative changes sign. So to find those, you just want to look for the point where the second derivative is 0 and check if it's changing sign. And that's the same as the concavity changing. Remember, we have our concave up and concave down, depending on the second derivative. Increasing and decreasing just depends on the first derivative. A function's increasing if the first derivative is positive, and decreasing if the first derivative is negative. This is super important, so we want to note that any local extrema, so minimum or maximum, has to be a critical point. But we have critical points that aren't either minimums or maximums. Now we also have absolute extrema. So those are the absolute maximum and minimum on some closed and bounded interval. So if we want to find that, we're going to find all the critical points. So an absolute maximum or minimum can occur at a critical point, or at one of your endpoints. So if you have an interval from A to B, and you're told to find an absolute minimum, you're going to find all the critical points between A and B, and you're going to check what the value of the function is at all of those critical points and at A and B, the endpoints. And whichever of those is the lowest is going to be your absolute minimum, and whichever of those is the highest is your absolute maximum. Sometimes we might have optimization problems. So you're given some constraints and you want to maximize something or minimize something. Often you want to minimize the cost while building something that has a certain area or a certain volume. And you can use calculus to write down a formula and then take the derivative because you're looking for a local max or min, or sometimes an absolute max or min. And so using this, you would take the derivative, set it equal to 0, and you can solve using that. Then we also talked about integration. So we have two types of integrals. The first is the indefinite, or the antiderivative. So all that is if we have a function f, we're looking for a function. So the integral of f is a function. So if you take the derivative, then you get f. Remember, once you calculate that, you need to add this plus c, because the derivative of any constant is 0. So adding a constant will not change the indefinite integral. We still have the power rule. So for example, if we wanted to take the indefinite integral of x squared, that would be x cubed over 3 plus c, because we always add our constants. In general, the integral of x to the n is x to the n plus 1 over n plus 1. Assuming that n is not -1. If n is -1, then we're going to have 1 over x, and then the integral is the natural log. In some simple cases, if you're working with a linear function, you can also just draw it out and look at the area. Sorry, once you're doing definite integrals. So a definite integral is just the area under a curve. If your graph's simple enough, you can just draw it and take the area. If not, the best way is usually the fundamental theorem of calculus. So say we have some function. F is some function, and we want the area under the curve of f from A to B. Then what we're going to do is we're going to find an antiderivative. Say g is an antiderivative of f. And then this integral equals g of b minus g of a. It's super useful. Let's do a quick example just to see that. So say we have f of x equal to x squared plus 1. And we want to find the integral from 0 to 1 of f of x dx. So the indefinite integral, well, we're going to get x cubed over 3 plus x. And we don't need the plus c because it's going to get subtracted off. And we're just going to go from 0 to 1, and that's going to give us 1/3 plus 1, which is 4/3. And we don't have to care about the value at 0 because it's just 0. So we also have the other fundamental theorem of calculus. So the one I usually call the first, which is that if you have a fixed point A and you take capital F of x equal to the integral from A to x of little f of x dx, then capital F of x is an antiderivative of little f. So that just gives you a way to use the definite integral to find an antiderivative. We talked about using Riemann sums. So the way to do that is we have a function, we can approximate the integral by adding up these rectangles. So for example, we could do a right sum, which means the height of the rectangle is always the function value on the right of the rectangle. We could also do a left sum. So in that case, the height of the rectangle would be the value on the left. Or we could do a midpoint sum. So we take the value in the middle. That's usually more accurate, but also a lot more work to work out. We could also always just do a lower sum or an upper sum. So that means we always just take whichever of the two side points is the lowest, or we always take the highest value. So all of those are valid ways to do Riemann sums. The question will usually tell you how to do that and how many rectangles to use. You should be aware of when a function is increasing or decreasing implies that the Riemann sum is going to be lower or higher than the actual value. And it's good to sometimes just also work out the actual intervals just to sanity check your Riemann sum, because the calculations do get quite tedious. And yes, sometimes you're going to have a question where you're not actually told the function value everywhere, then you do just have to use the Riemann sum. And this is an example of such a problem. So it would give you maybe like 4 values of x and f of x and tell you to use a Riemann sum with 4 integrals or 4 boxes, with just a left sum or a right sum, or right, there's a trapezoidal sum, which I did not go over. But what this does is you have 4 points. And this, you're not exactly using boxes, but you're going to go 1, 2, 3, and you're going to basically be averaging like this. So that's also something you could be asked to do. Here's the general formula. You can actually use Riemann sums to calculate an integral by taking the limit as you take more and more rectangles. That's not the nicest way to do it. Usually you just want to use the fundamental theorem of calculus if you can. Here's the trapezoidal sum. So yeah, you're just, the formula's over there, but intuitively, you're just connecting each point you have. And you're basically making this not exactly a trapezoid if there's a lot of terms, but just simpler shapes. That's like a triangle and a rectangle that you can add up. And those also tend to give you a pretty good approximation. Just good to keep in mind, I was in fact asked this on my AP exam. If a function's concave up, then the right Riemann sum is an over approximation, and the left Riemann sum is an under approximation. While if it's concave down, the opposite is true. Then the right Riemann sum is an under approximation, the left is an over approximation. So if you did want to do the definite integral with Riemann sums, then here's your formula. Or you can use the fundamental theorem of calculus. We've got the power rule for any derivatives and the fundamental theorem of calculus. This is part 2, where we use the antiderivative to find the definite integral. And sometimes you might be asked to find an integral from a graph. And in that case, you would have to just add it up. So for example, if you want to find the integral of this one, we would add the area of this triangle. Then we would subtract the area of this hemisphere. That's because it's below the x-axis, and we would add the area of this triangle. And that's how we would get the integral from, say, 0 to 35. A lot of nice properties hold. You can pull constants out of integrals. You can add and subtract them. Products and quotients are not that easy. But if you have something weird, then you want to look for ways to use a U substitution or integration by parts usually. We have a lot of integrals of trig functions, which are good to memorize. I'll leave that up for just a moment so you can copy it down if you want to. we talked about ways to integrate. So we have u substitution. So we're going to take some part of the function we're integrating. We're going to replace that with u. And then we're going to find du dx. And because we need to rewrite the integral as a du integral and have everything in terms of u before rewriting it. And then we can integrate in terms of u instead. There's also integration by parts. So the formula for that, just remember, is the integral of u dv equals uv minus the integral of v du. Sometimes that takes a bit of work to figure out which parts of the function you want to be your u and your v. Won't always work, but it's sometimes very helpful. Sometimes if you have some polynomials, you can also like try and split it as a sum. You can use like partial fractions, that can help. Here's our integration by parts formula. And here's some useful hints. So the functions we want as u are of these kinds. We want logarithmic functions, inverse trig, polynomial algebraic functions, trig functions, and exponentials. Those are often good candidates for your u. And the stuff that's left is often a good candidate for v, or for dv, and then you would want to find what v has to be from there. Sometimes you can like draw this table with u and v and du and dv, just so that it's easier to write down the formula. Partial fractions, we haven't really gone over that, but if you have something that looks like this, you can try and split that into a sum of things that are easier to integrate. There's also improper integrals, which is when your limits are not real numbers. So you can have an infinite limit, or you can have just a number, but where the function goes off to infinity. And then basically what you're going to do is take a limit so you're going to find the integral from a to b, and then you're going to take a limit as b goes to infinity of that. And we haven't really talked about differential equations, but the way this is going to work, you're going to have some equation in terms of dy dx. And basically what you're going to do here, you're going to move the dx over. It's hard to explain why that works, but it does actually work. So you're going to have dy equals 2xy dx. And you want to move all the y's to the same side as the dy. So I'm going to actually make that a 1 over y dy equals 2x dx. And then you just slap an integral sign in front of both of them and you integrate. And then you set the two sides equal to each other, and then you can solve for x and y in terms of each other. So I think that's it. So basically we did limits and continuity, derivatives, methods for differentiation, especially the chain rule, but also the product and quotient rules are important to remember, and some special derivatives. Then we had integrals, the indefinite integral, which is just the opposite of the derivative. Given some function, you want to find another function whose derivative is the function you started with. Then we have definite integrals, which is the area under the curve. We related them with the fundamental theorem of calculus. And we learned some new ways to take integrals. We have u substitution, where you plug in some function of x for u, and rewrite the integral as a du integral. We have integration by parts. We have the mean value theorem, Rolle's theorem, the intermediate value theorem, the extreme value theorem. And we also talked about rotated solids, how to find those volumes using an integral. So we're basically, if we have some shape that we're rotating, say we're rotating this, we're going to look at the area of every circular section and integrate that. So that's going to be like pi times the function squared, and we're just going to integrate straight across. And that's going to tell us how to find the rotated volume. We have a little bit of time, so let's just do one practice problem. Let's say we have f of x equal to e to the 3 times the natural log of x. What is f prime of x? So just remember the chain rules. Should be pretty simple. All right, so our outer function is e to the x, and the inner function is 3 times the natural log of x. So the derivative of e to the x is e to the x, and we're going to substitute in 3 times the natural log of x. So that's e to the 3 ln x times the derivative of this thing inside, so times 3 times 1 over x, so times 3 over x. That's going to be our derivative. And let's do one practice integration problem as well. So let's say, what is the integral from 0 to 1 of e to the x plus 2x cubed dx? All right, let's go over it. So we want any derivative, and then we're going to go from 0 to 1 and subtract. So the any derivative of e to the x is just e to the x. And then for 2x cubed, we're going to go 2 times x to the 4th over 4. That's just x to the 4 over 2. And then we're going to go from 0 to 1. So we're going to evaluate at 1, evaluate at 0, and subtract. So this answer is going to be e to the 1 plus 1/2 minus e to the 0 plus 0. So e to the 0 is 1. So this is e plus 1/2 minus 1, which is just e minus 1/2. And that's all I got. So thanks so much for watching. And that's all. Yep.